Hi everyone and welcome back to PrepFusion. So today we will start the lecture 2A of this phasor diagram chapter. So we have only learned about basics of sinusoids, what are phasors, those things, but we have not learned about circuit components. How does a circuit behave when there is a sinusoidal input? So that is what we will learn. Before that, we will discuss about DC circuits. So if I have a DC circuit, how will it behave? So in case of DC circuit, right, for a resistor, we already know the voltage will be like voltage is some constant voltage, that is 1 volt, and current is also 1 amperes, correct, in this particular case. So is there is any phase displacement between voltage and current? No. So for DC in steady state, I am discussing about steady state, this will be 1 volt only, correct, this will be 1 volt only. So the current and voltage will does not have any phase difference. Now here in capacitor, yes, initially if you say me that initially I am applying a 1 volt across a capacitor, we should never do actually, we should never apply a constant DC voltage across a capacitor, then a high impulse current will flow and that will instantaneously charge the capacitor. Voltage will still be 1 volt, correct? Impulse current will flow, that may damage the capacitor, that is for other discussion, but voltage will settle to 1 volt and then current is 0. Current is simply 0, right? It has reached steady state, current is simply 0. We cannot talk about any phase relationship, right? Here what is happening, if I place 1 volt, yes, what will happen, it will never settle basically. If VL is 1 volt and I know that what is inductor voltage VL is equals to L DIL by dt. So simply if I integrate on both sides, because VL is constant, it will be 1 by L, that is 1 into T, so it will be T. So your IL, right, IL of T will be simply equals to T. So it will be just like a ramp function. This I hope Himanshu has already taught you. So here, right, can we discuss anything about phase? Like my voltage is some like input voltage is equals to my inductor voltage only, that is a constant value of a step, that is 1 volt, and my current is basically a ramp. Can I discuss anything about phase? Phase came where? Phase came where I had sinusoids. So there is no concept of phasor in DC circuits. There is no concept of phasor in DC circuits. That is what is written over here. Okay. So it does not matter if your impedance is like is AC impedance. I will discuss about this, Z angle theta. How do we write Z angle theta? All those things I will discuss. But it does not matter if you have applied a DC input. There is no concept of phasor. Simply solve whatever you have learned before this, right? Before AC. Just that much knowledge you will require and you will be able to solve the circuit. You don't need any AC knowledge to solve DC inputs. For AC inputs, of course, you will need the AC knowledge. So that is what we learned. So if I change the supply now, if I change the source, then things will be very, very different. Okay. So in AC circuit analysis, phasors are used to represent sinusoidal voltages and currents, making it easier to analyze their phase relationships. Here we explore the phasor relationships in series RL, RC and RLC circuits. Okay, so that is in today's lecture we will discuss about series RC, RL and RLC circuits, but first we will discuss about individual elements RL and C. So if I have a resistor connected across a sinusoidal input voltage, this is my voltage V of t. What will be the current? Like what is the voltage across the resistor? VR of t is same because it is directly connected across the resistor. It is simply V of t, that is equals to 5 sine of omega t. Okay, this is my Vt of t. And what about the other one? What about the current? Current, right? For a resistor, I know the relationship between current and voltage for a resistor. It does not matter if it is time domain or something. It is simply V equals to I of R. Correct? Current across a resistor. So R they have given me as 5. So your IR of t will be VR of t divided by R, that is 5. So it will simply be sine omega t. Okay, this will be your current. So my current waveform is a sinusoidal function. My voltage waveform is also sinusoidal function. Here, right, we can discuss about phasors. If I have DC input, there were no sine functions, so no discussion of phasors. Here I have sine functions, so now I will discuss about phasors. So here what I observed is that what is the phase difference between these two quantities, this has a phase difference of 0, this also has a phase difference of 0. So there is no phasor difference, right? There is no phase difference. So if I assume my sine omega t to be reference, this will be 5 angle 0, this also will be 5 angle 0. So not 5, sorry, only 1 angle 0. So basically for resistive network there is no phase difference. So that is what I have written over here. In purely resistive circuit, the voltage and current are in phase, meaning they peak and cross zeros at the same time. Okay, basically the peak will happen at the same time and the zero crossing will also happen at the same time. Now of course the peaks will be different, right? Because current peak we are dividing by resistor, so peak value will be different depending on the resistance value. But the peak will occur at the same time and the zero crossing will also occur at the same time. That is what we mean by if two voltages are aligned. So phasor diagram shows there is no phase difference. So how do I draw the phasor diagram? So okay, this, right, IR should be here. Okay. Yeah, IR is here. How do we draw the phasor diagram? So the phasor diagram will be something like this. As there is no phase difference, if I take the voltage as reference, okay, sine omega t as reference, this is reference, okay. So here is my voltage signal, 5 angle of 0. Current also will be in the same phase, 1 angle of 0. So this will be my current and this will be my voltage. So both of them will be in the same phase, that's why in the same, along the reference, they will be along the reference only, okay. Just important point is, it's not like always they will be along the reference. Reference might be something else. You can choose reference something else. You can choose here, if I would have chosen reference to be my cos omega of t. Let's choose the reference to be cos omega of t. Okay. So if I choose the reference to be cos omega of t, so how do I convert this sine into cos? How do I convert this sine into cos? So I can write this, right? This can be written as 5 cos omega t minus 90, cos omega t minus 90, right? This is what we can do, correct? So now I can convert this into phasor. So with respect to my reference cos omega t, it is lagging by 90 degrees, so this will be 5 angle of minus 90. Here also with respect to the reference, again this is cos omega t minus 90. Again with respect to the reference, this will be 1 angle of minus 90. 1 angle of minus 90. Now, right, if I draw the phasor diagram for this, so my reference is here. This was for the sine omega t. Okay, I will draw another phasor diagram for cos omega of t. So now my cos omega of t is the reference. But your voltage, it is lagging, right? So if it is lagging, right, I will not have space over here. So what I will do, how do I get space? So basically I have to add another page. Unfortunately, we have to use another page. So for a lagging, this is lagging, right? This is lagging, this both are lagging only, minus 90 lagging only, but amplitudes are different. So voltage will have an amplitude of 5 angle minus 90, okay, and currents will have amplitude of 1 angle minus 90. Okay, so are you noticing something? Yes, it is not with, like, it is not aligned with the reference, but still your currents and voltage are in the same phase, right? Same line. So what do you understand from this? Like this, I hope this second point is clear now. The phasor diagram shows the current and voltage will be aligned. It is not necessary that it will be on the reference only. Okay, it can be something else as well, but depends on what reference you choose. So here we have chosen reference as cos omega t. So that's why voltage and current will be in the same phase, but it is not in with reference. That is fine. That is fine. But voltage and current must be in the same phase for a purely resistive network. Okay, that was for the purely resistive network. So I hope you have understood this point. What I will do, right, I will take this one as well. to the next page. That would be better basically to do a comparison. Okay, so let me do one thing. Okay, so if I do paste this here because the heading is important. So yeah, now it is fine. So now I hope you have understood about purely resistive network. Now let's discuss about purely inductive network. From here your AC, actual AC starts. Okay, so I'm taking a current source because it will be easier to calculate. If I take a voltage source, like it will be bit like the integration will be bit complicated. That's why we are ignoring the voltage source. Ultimately final answer won't change, and let's not go into like complex things from the starting itself. So I know inductor has this relationship, that is VL of t equals to LDIL of t divided by dt. That is the relationship between the inductor voltage and current, right? What is this? This is the instantaneous current. This is known as the instantaneous. So in AC, right, they can ask you the instantaneous value as well, or the RMS value. RMS we will discuss, but instantaneous means it will be a function of time, and at a particular time what is the value of that quantity. That is what instantaneous means. This is the instantaneous current, and this is the instantaneous voltage. Okay, so now here you can write that what is the current, right? I'm giving 5 sin omega t, that is the current. So it will be L is 5 in our case, or let's keep L for now, L into DIL of dt. So that is ddt of 5 sin omega t, and this is my inductor voltage VL of t. So this will be equals to VL of t will be equals to, this omega is a constant, I am differentiating with respect to t, this will be 5 omega will be constant L into cos of omega t. So what you notice is that this 5 cos of omega t, right, this 5 cos of omega t is what? This 5 cos of omega t is the current, right? So not current, sorry, no, this is not current. So basically, right, what is current? Current is 5 sin of omega t. So let me write it in terms of current. Let me write it in terms of current. So if I want to write this in terms of current, this VL of t will be equals to 5 omega L sin 90 plus omega t, correct? This was the relationship that I have told you previously as well. So cos omega t can be written as sin omega t plus 90. Okay, so this will be equals to, this will be equals to so from here what we can say, can we convert this into phasor? Can we convert this into phasor? So if I convert everything into phasor, right, this will be VL of S or J omega, whatever you want to say, VL of S. Okay, I'm converting everything in terms of phasor. This, right, will be converted into what? This is sin omega t plus 90. This is sin omega t plus 90, or this I can write 5 angle of 90, correct? This I can write as 5 angle of 90, or what you can like what you can write, there are other ways as well, that your current is 5 sin omega t, your current is 5 sin omega t. So what you do is you can write in phasor, what is the phasor quantity? That is, it is 5 angle 0, because sin omega t is my reference. Okay, if I want to write this in terms of my current, what can I do? What changes can I do? If you remember, one thing I have told, that if I multiply 1 angle 90 into 5 angle 0, basically the angles will get added, correct? And what is 1 angle 90? What is 1 angle 90? 1 angle 90 is G. This we have learned in basics. That's why basics is very, very important. 1 angle 90 is J. And what is 5 angle 0? 5 angle 0 is, according to us, we know internally it is simply I. This 5, it is 5 sin omega t, which is simply I. So this will be I of S in the frequency domain, because it is a function of frequency. Okay, if you don't understand S, you can ignore S for now, that is not important. Just for proper notes I have to write everything. So for S is basically the Laplace domain variable. Okay, so this will be J I of S, and of course there is a omega L here. This omega L I did not take, I just taken 5 sin omega t plus 90. So this will be J omega L I of S. Now if I write VL of S over I, this is L, inductor current only, IL of S, you get the relationship like this, that is J omega L. That is what you get, or which you already know if you have studied from Himanshu. I think he has taught that it is simply equals to SL. If you convert in Laplace domain, it is simply equals to SL. So that's why we replace S with J omega. And you know, this is called what? This is called as the steady state inductive reactance. Why steady state? Because we are discussing about steady state, because initially there will be some AC transient. During that time, the reactance provided will be different. The reactance provided will be different. Steady state means we have reached steady state, and we are discussing about the sinusoidal steady state response that I have taught in the previous lecture. So this J omega L is known as the sinusoidal steady state reactive or reactance offered by the inductor. Okay, so whenever we write S equal to J omega, that basically means we are discussing about the frequency response. We are discussing about the frequency response. Okay, that's it basically. So yeah, I hope you have understood this portion. Right now, let's basically are there few more points? Yes. So this was basically the Laplace. So now the phasor. So what does this J represent? This J has a significance. So from here only you can understand what is the significance of J. From here in this equation, if you see that if you can, we have converted this into current, right? This is your current. So basically your voltage has a phase of plus 90. So your voltage is leading IL by 90, or other way around you can say your current is lagging VL by 90. That is what you can say, right? So generally that is what we say, that current lags the voltage in case of a inductance. In case of inductance, the current lags the voltage across the inductor. It is the same across the inductor. So how will we draw the phasor diagram? So if I have chosen sin omega t to be my reference, so sin omega t is here, sin omega t is here, that is my reference, sin omega t, and here is my current, right? It is in phase with the current because my current is also 5 sin omega t. Current is also 5 sin omega t only. So it is 5 sin omega t. Okay, and what about the voltage? Voltage will be plus 90 because it is leading. So voltage will be, either you can write from here J into IL. J means I am going in the clockwise direction. Whenever there is J, multiplication of J, that means what? J is what? J is 1 angle 90 plus 90. So if I am multiplying J, that means I am going in the anti-clockwise direction by 90 degrees. So this, right, you can write it like this, both way works. This will be your voltage. Okay, either you can write J into I, or you can write that it is leading. It is basically leading. This is my VL, that is leading. It is cos, like some proportional to cos of omega t. So that's why it is leading. Or generally what, like most books show you that they take the voltage as reference. So they will take the voltage as reference. Okay, here in the x-axis, VL of, this will be my VL, and current will lag by 90 degrees. So they will show it like this, that here current lags by 90 degrees. Okay. IL of t into V, not T actually, this is phasor, right? So no, not this. So this will be IL. So here this will be the angle 90 degrees. Okay. So voltage is here and current is here, right? Now I hope you understand, like this is the normal phasor diagram that you see. So there are two ways to write. First way is the one that your VL leads IL by 90 degrees. This you can write, or you can write the second point, that is your IL lags VL by 90 degrees. So basics have been cleared. So I hope there are no doubts in these lag, lead, plus 90 minus 90. That's why we have done basics very well. So this JIL, and of course there is a term factor, that is omega L. This omega L is the reactance, right? This JIL, sorry, this is multiplying by J omega L, right? Yeah, this should not be divided, this should be multiplied. Yeah, this factor will be multiplied. J into omega L is just a constant, that's it. Okay. Or what you can do with voltage, right? If you multiply minus J divided by omega L, you will get current. Okay, both way works. Both way works. There is like not a right thing or wrong thing. Both are same only. Okay, here as well, both statements are correct. So the summary is written over here. In an inductor, voltage leads the current by 90, or you can say that the current lags the voltage by 90. Now it does not mean that voltage leads the current by 90, that it does not mean if I, even before applying the current source, I will see the voltage source. I will see the voltage across the inductor. No, it does not mean that without applying any current to the inductor, as soon as I move closer to the inductor with a current source, inductor understands, okay, like Anish is coming with a current source, let me produce a voltage now. No, it cannot predict the future, right? What if I don't connect? What if I don't connect? I scam the inductor that no bro, I will not connect, I will take out. So it is not like that. It is not the concept that voltage is leading the inductor current, that means that voltage waveform will come first, then the current waveform will come. No. Both waveforms start at the same time only. That is correct. Both waveforms will start at the same time as soon as the supply is applied, but the zero crossing points will be different. The inductor voltage will have earlier zero crossing point than the current. Why? Because voltage leads the current. So I told you what does lead and lag mean in the previous lecture. So those things are clear. So again I will reiterate here. So voltage and current across the inductor will be same. Across the inductor will be generated at the same time as soon as supply is applied. Either voltage source or current source, does not matter. As soon as supply is applied, then only the voltage and current waveform both will be generated in the same time. But the zero crossing points, ZCP, zero crossing points of voltage will come first, come before current, or the peak values, or you can say the peak values come before inductor. Now this, right, whatever I am discussing with respect to the inductor voltage and inductor current, I am not discussing about supply. I will reiterate this, inductor current. Okay, so this, right, I can write it here, this can come here. So with respect to the inductor voltage and current. So this is the first point. Second point I will write here is whatever I am discussing with respect to the inductor voltage and current. If I am discussing inductor voltage leads the current by, the voltage leads the current by 90 degrees, that means I am discussing about inductor voltage and inductor current, not about the supply. Okay, I am not talking about the supply. Yes, here the supply current and the inductor current both are same, but after a certain point of time they will not be the same. They will not be the same. But one thing will be same, that the inductor voltage and the inductor current, they will have that phase relationship, that the inductor current lags the inductor voltage by 90 degrees. Please keep in your head. Don't confuse with the supply. Okay. So here I will write the second point. We are discussing with respect to inductor voltage and current. So whatever we are discussing with respect to inductor voltage and current. Okay, just keep that in mind. I hope that is clear now. So mathematical representation, yeah. So mathematical representation, VL will be equals to IL into XL. That is, what is XL? XL is the sinusoidal steady state inductive reactance. So this XL is defined as steady state. XL will be inductive reactance only, but this omega L, right? Omega L will be defined as steady state inductive reactance. Why steady state? I hope you know, because initially there is some transient, and during that phase of time the reactance will be offered, will be different, but at steady state this will be the reactance offered. That is equals to omega into L. Omega is the frequency, so it is a frequency dependent term. Okay, so either you can write the phasor diagram shows VL is ahead of the current, or you can write IL lags VL. From this diagram also you can see zero crossing point of VL is happening first, then the zero crossing point of IL is happening. Okay, so actually your current waveform, okay, current, we have the current waveform is this. Okay, yeah, so your, okay, this is something wrong, this is wrong, this is not the correct one. So your current waveform is actually, yellow one is your current waveform and green one, sorry, blue one is your voltage waveform. How do I cross verify? So okay, something is wrong this, right? Your voltage is cos omega t, 5 omega L into omega cos of omega t. So it is cos of omega t, right? So cos of omega t starts from 0. Actually bit of mistake we have done. So this, right, basically will be starting from here. Yes, that is my mistake. So I can edit few things out. So this will be here, and in here it will go on till here. Yes, now it is totally fine. So if we see, this is my voltage, right? Blue is my voltage and current. Okay, don't care about the amplitude right now. I don't care about the amplitude right now. So the zero crossing, right? Yes, here zero crossing once is happening, that is fine. You can ignore the this point. After this point, right, I see the zero crossing is here. After that, zero crossing is happening over here. Again, like this goes down first, then the current waveform goes down. So we have to, like, it is also a sinusoid, right? So the difference is first this goes down, then the sinusoid goes down, or you can see the peak here is happening first, then the peak across the current is happening, right? This is the cos omega t. I hope you know how to plot the cos omega t. So basically there is a phase difference of the peak. If you want to see the peak as well, the phase difference is simply pi by 2. The phase difference in the peak is simply pi by 2, or if you want to see the zero crossing point, first this one is going down, then the current waveform is going down. Okay, so there is a difference of pi by 2 radians or 90 degrees, whichever one you want to say, and this time is just a certain time after transient. This is the start of the steady state. So where this is just an observation point, this is not t equal to 0, just an observation point at steady state. So this is observation point, start of the observation point, start of observation at steady state. Okay. So yeah, I hope you have understood this portion. So let's now discuss about capacitive networks. So capacitive networks, again I am applying a voltage. Now we will do a bit fast. So I know the relationship between capacitor, current and voltage, that is IC of t equals to C dVc of t into dt. So my, what is my IC of t? IC of t will be, which is equals to my I of t only in this particular case, that will be equals to C into Vm, like V is what? V is 5 sin omega t. So differentiation will be C omega into 5 cos of omega t. Okay. So this is my capacitor voltage. Now again, if I want to convert this into with respect to reference, right, this can be written as C omega 5 sin omega t plus 90. Again, if I want to convert this into the Phasor format, this will be converted into IC of S. This will be C omega into 5 angle of 90 degrees, and I can write this IC of S will be simply C omega into J VC of S. Correct? How am I doing this? In the previous example, we have already discussed about this. So now if I want to find out the inductive reactance, what will be my XC? XC will be the voltage upon current. So inductive reactance will be voltage upon current, that is 1 by j omega c, that you already know. I know from DC you have already learned about this. It is simply equals to 1 by S. You replace S with j omega, 1 by SC, you replace S with j omega, you get back to the capacitive reactance. Okay, pretty straightforward, pretty simple. What about the phasor relationships? So phasor relationships, what I see, observe, is this time it is opposite. So this time this is my current, and current is leading the voltage, because voltage is 5 sin omega t and current is cos omega t. Correct? So current is leading the voltage. So voltage is here. Okay, this is my voltage, this is my reference. This is my voltage, and current will basically lead, the voltage. This is my VC and this is my current. Okay, so don't write T here, over here, these are all phasor quantities, don't write T. This was the relationship between voltage and current. If I want to, like, let's say, what is my IC? IC you can write like this. It is j omega. J I am multiplying because I am going in the anti-clockwise direction from VC. That's why j multiply omega C. That is the capacitive. This is not the capacitive reactance, right? Capacitive reactance is 1 by j omega C. Remember that capacitive reactance is 1 by j omega C into VC basically. From voltage, if I want to write, come back to this, I have to multiply j. That means I have to move in the positive anti-clockwise direction. Okay, I hope you have understood this point. These are the phasor forms of a capacitor. This is the phasor form of a capacitor. Other way around also you can write. You can write the IC here first. Okay, IC can be written here first as the reference, and your voltage will simply lag the current. So two ways you can write. First one is that your IC, capacitor current, leads VC, that is voltage by capacitor voltage by 90 degrees. Or what you can write, your VC lags capacitor current by 90 degrees. Both are same. Okay, there is no difference, both are totally fine. So same thing we have written over here itself. So this, right, we have to change the waveform a bit. So this will be here and here. So if we see, like, this time this is my current waveform and this is my voltage waveform. So voltage is attaining its peak here, but current has attained its peak earlier. So current obviously has attained its peak earlier, so current will lead. Here current is crossing 0 at this point of time and going to negative, and voltage is going to negative after what? Pi by 2. So that's why there is a phase difference. There is a phase difference of pi by 2, And this time it is quite the opposite. Phase difference is that my voltage is lagging the current, that is current is leading the voltage. Remember, again I want to reiterate, this voltage and current are not supply currents, not supply currents, because many students I have seen they get confused. This is not supply current, this is the capacitor current. Capacitor current and voltage, whatever we are discussing with respect to the element, capacitor current and voltage. Okay, again what is this? This is the steady state reactance. Okay, this is the steady state reactance. So here IC will come before VC, but not like it will, like I'm not even applying supply and it is coming. No, both waveforms are there, both waveforms are there, but the peak of IC. So what is the importance here? The peak of IC or the zero crossing points will come before VC. Okay, so I hope you have understood these points. So like the summary is written over here, you can go through and read, like the angle, the phase of voltage and currents, it is written, like how do they behave at high frequency, at low frequency, like if you make omega tending to infinity, how will they behave. So all this you already know. If you don't know, like you can put the values of omega and check. Okay, and basically one more thing is there, these are the impedance, or like if only single element is present, this is known as the capacitive reactance, this is known as the, sorry, this is known as the inductive reactance, and this is known as the capacitive reactance. There is a term known as admittance. Admittance also has two terms, one is conductance and susceptance, that is written over here. Okay, it is just the inverse of impedance. So the conductance is the what? It is the resistive part, right? Resistive part, and the susceptance is the reactive part. So that is what is written in G is the conductance and B is the susceptance. So the homework for you is, if let's say I have a impedance Z equals to R plus Jx. Okay, so the admittance will be what? Admittance will be like Jx is just a reactive component, it will be the sum of both capacitance or what do you say, capacitance and capacitive reactance and inductive reactance. So your impedance, your admittance will be, basically your admittance will be equals to 1 upon R plus Jx, 1 upon R plus Jx. This will be your admittance basically, correct? Can you convert this into this format? What you have to do, you have to simply do cross multiplication, R minus Jx and R plus Jx into R minus Jx. So I am anyways doing it, but just convert it into this format and identify the G and B separately. So like if you do solve the equation, you will get, you identify the B and G to be this R by R square plus X square and minus X by R square plus X square. Just one thing you keep in mind, generally students get confused with this thing, that your conductance will be simply inverse of resistance 1 by R. No, it is not inverse of resistance. When will it be inverse of resistance? If the reactive component X is equal to 0. If X is equal to 0, that means this is gone. So 1 by Z will be Y, Y will be simply 1 by R, X is 0. So then I have only real component, then your G will be simply equals to 1 by R. Only then, otherwise it will not be the case. Again here as well, many students get confused, they write the susceptance to be inverse of reactance. It is not always the case. It is not always the case. When it will happen? Again, same condition. If this time my R resistive component is 0, then my susceptance will be simply 1 by X. How it happens? So if the resistive component is 0, this becomes 0, right? This simply becomes 0. So then my susceptance is 1 by Jx and minus sign will go up the top. So this side will not be equals to 1 by X, this will be minus 1 by X, okay? Minus 1 by X. So just be careful regarding this. Generally students get confused, right? Yes, it will be equals to minus 1 by X, but when will it happen? It will happen when your R is 0, otherwise it will not happen simply, okay? So here like few key points I want to say. Like we will discuss this later as well about reference, what to take reference or what not to take reference. So one key point is there in series circuit. Generally, this will be the general trend, but you have to be smart. With question practice, you will understand what you have to take the reference and what you don't have to take the reference. Because like if you choose a reference, right, that basically describes how you will calculate the question. In AC, I'm talking about AC. So in AC, reference is very important. The same question, if you choose a very bad reference, it can take you 10 minutes to solve, and the same question can take you 1 minute to solve if you choose a good reference. Good reference is that reference that is connected to most of the circuit elements. That I will discuss later on, don't worry. But just try to follow this general trend that in series circuit, the current will be considered as the reference phasor, and in parallel circuit, the voltage will be taken as reference phasor. That's it. In series circuit, the current will be considered as reference phasor, and in parallel circuit, current voltage will be taken as reference phasor. Why? Let me give you an example. So this is simple R, L and C element, and I have a sinusoidal input here. So this is Vc, this is VL, this is VR. Okay, and this is my input Vs, Vin, and this is my current. So which component here, which signal is common between all the elements? Current. I is common with respect to the supply, with respect to the resistor, with respect to the voltage, with respect to the capacitor. So which one should you choose as reference? Current. That's why it is written in series, choose the current as reference. Same, just take example of a parallel circuit. You will see voltage is common across all the elements. That means there you have to choose the voltage. Okay. One more thing is that, if you observe that here the capacitive reactance came out to be negative, correct? It was minus J, so it is lagging. That is, it is in the clockwise direction, and your inductive reactance came out to be positive, plus J. So if it is a linear and passive network, so here, right, this is discussed about like this region is for linear and passive network. In a linear and passive network, your resistance cannot be negative, correct? Your resistance cannot be negative, your resistance can be positive only. So you will be lying either in quadrant 1 or quadrant 2. That's it. So this is for the region linear and passive. Okay, linear and passive. Okay, so if I have a linear and passive region, in this region, so my x can be positive or negative. If it is positive, I'm talking about impedance. This is the impedance plane. Okay, impedance plane. For admittance, it will be different. Impedance plane. So if the reactance is positive, that means this region is for the inductance. That means it is a inductive reactance. If the reactance is negative, that means it will be a capacitive reactance. Now what can be the limiting values? The maximum and minimum values of reactance. So this is my theta z. Okay, theta z can be maximum, it can be plus 90, minimum it can be minus 90. Why? Maximum I can lie here, that is I don't have any resistance, it is purely inductive, and minimum is minus 90. I can lie here. Can I go here? No. It has to be active then. It cannot be passive network, it has to be active network. For active network, resistance can be negative, but theta z is the impedance angle. So basically it is the like impedance of, generally the impedance of a passive network. So this theta z limiting values are with respect to passive network. If it is a passive network, then my theta z range, passive and linear network, then my theta z, that is this is known as the impedance angle. So this, right, later on more we will come to this more, but for now you understand this is the impedance angle, r plus jx, tan inverse x by r. How to find out the angle, I hope you know till now. So basically it is the impedance angle. Impedance angle. So now let's come to the series RL circuits. So in series RL circuit, now we know what is the inductive reactance. So I will solve using basic KVL. So I will apply a KVL across the whole loop. If I apply KVL across the whole loop, let's say this is my Vs, okay. So my minus of Vs plus Vr plus VL equal to 0, correct? Or I can write Vs equals to Vr plus VL, or what I can write is Vr is equals to I into R plus VL, that is equals to I into what, JXL, correct? Because it provides a phase lead of 90. So it will be, I will replace my VL with I into JXL. This, right, I have taught previously here. ZL will be equals to I into JXL. So here, right, VL, actually I should have written VL in phasor component, this will be J times XL, and here as well your VC will be what? VC will be minus J times XC. Okay, just be careful regarding this. I don't have space. So what we can do, right? This we can reduce. Minus J IC into XC. Okay. So that is the case basically. So here, right, same thing what we will do is your VR will be IR into plus JXL. So which is equals to, what is your Vs? Like how do I find out the Vs and VL, all those things? So from here, right, Vs is what? Vs is Vm sin omega t, correct? So for now I will write here, for now I will write just V only, and this is I. So if I divide by I on both sides, this will be R plus JXL. So this is V over I, that is your Z impedance. This is V over I, that is your Z, that is impedance. So impedance will be R plus JXL, because this is a simple series circuit, simply the reactance gets added. That is established. Next thing is about the voltage. So your voltage will be what? So the magnitude of V should be equals to this, right? Magnitude of VR whole square plus magnitude of VL whole square. Why? Why? Because both of these are with a phase shift of J, correct? Both of these are with a phase shift of J. This has a phase shift of 0 with resistance, because the current and the voltage across the resistance will be in the same phase. So I and voltage, both of them will be same phase. So this is V of angle 0. This has an angle of plus 90 with respect to the current, because I have not told you current is my reference. So with respect to the current, this has an angle of 90, correct? Because it will lead the current by 90 degrees. Current is same for all the elements. Okay, basics, clear the basics. If you are having the doubts, clear the basics. So that's why the magnitude of the voltage is VR square plus VL square, and the angle of the voltage, both are in the first quadrant only. It will be simply tan inverse VL over VR. Okay, so this will be the voltage value. So if I want to draw the phasor diagram, of course phasor diagram will come later on as well, but if I just want to draw the phasor diagram right now, this is my VR. So first, right, in a phasor diagram, if it is a series circuit, I will first draw the current, because current is my reference. So I will first draw that. Then with respect to the current, where is the voltage of the resistor? Resistor will also be lying in the same phase across the current of the voltage. And through the current, the inductor voltage will lead by 90. This I have taught in the previous portion of this video. So voltage will basically lead the current. Voltage will lead the current. That's it. Voltage will lead the current. Okay. Voltage will lead the current. So from here also you can identify the same thing only, that it is VR square plus VL square. Angle is tan inverse VL by VR. Same thing. Same thing. What about the impedance, sir? Impedance is this, right? V by R plus JXL. So impedance, same thing I will write here. Okay. I will say something in the next slide. So impedance will be what? This will be Z angle of theta Z. So magnitude of Z, that is amplitude, it will be equals to under root of R square plus XL. L whole square, and angle of Z will be simply, or theta Z, angle of Z or theta Z will be simply equals to tan inverse XL by R, tan inverse XL by R. Okay, that will be your angle of Z. Now, one very simple basic question you will have doubt. Let's say this voltage is 3, this voltage is 4. Then if you apply KVL, right? You know KVL is the sum of the voltages. So you directly write here that your V will be equals to 3 plus 4. That will be equals to 7, and this will be absolutely wrong. Is KVL incorrect? No, KVL is correct. KVL is correct. What is incorrect is you are simply doing the algebraic sum. So algebraic sum you can only do in DC circuits. You can only do in DC circuits. In AC circuits, you have to do the vector sum or the phasor sum. Vector, this is algebraic sum. Here you will do either vector or phasor sum. So what is vector or phasor sum? So vector or phasor sum, basically this is what? The voltage across the resistor will be in the same phase only, that is 3 angle 0, but the voltage across the inductor will be leading by 90 degrees with respect to the current. So this will be 4 angle 90. It will not be just 3 plus 4, right? So ultimately the value comes out to be 5 angle 53.13, because I remember what is tan inverse 4 by 3, that helps me. Okay, I also recommend you remember that thing. So this will be the voltage, this will be the magnitude, that is 4 square plus 3 square under root, and the angle. Okay, I hope you simply do not add that same thing. So impedance angle, I hope it is sorted. So if I draw the impedance triangle, right? So impedance is Z equals to magnitude of Z into phi Z. Phi Z is the impedance angle, basically impedance angle, and this is the impedance triangle. This is also known as the impedance triangle. Still it is not a triangle because I have only two sides of the triangle. I will draw the third side. So what is the third side? Third side basically, right? This is my R. R will be in the reference, and with respect to R there is j omega L, because it is plus 90. So it is in the anticlockwise, and if I add these two vectors, I will get my impedance. So this will be my impedance angle. Okay, this will be my impedance angle. So that is how we understand this thing. This is basically the impedance triangle. If you never heard of it, so now you know this is the impedance triangle. Here the interesting fact is, for an inductive load, phi Z will always be greater than 0. So phi Z will always be positive for a inductive load. If it is like overall resultant inductive load, then no matter what, the impedance angle will always be positive. So what is this impedance? Impedance is basically the impedance seen from the equivalent impedance seen from the supply. So it is R and L. These two components are there, right? XL and R. Okay, so this is just like a equivalent resistance. Just instead of resistance, we have a phasor quantity, inductive reactance as well. That is there. Inductive reactance is also there. Okay, we have the phasor quantity, inductive reactance. Okay, so that is one thing. So yeah, now like this is the phasor diagram which I have already discussed. So I will draw the phasor diagram in a better manner, and I will also discuss about what power factor. So we will discuss about power factor as well. What is power factor? So my phasor diagram, my reference, right? It is a series circuit. As it is a series circuit, reference will be current. As it is a series circuit, reference will be current. Okay, so my reference is current. So this is my reference, basically reference, that is the current. Now the voltage in the like the voltage across the resistor will also be in the same phase. Here voltage across the resistor will also be in the same phase, VR, angle of 0, and the inductive voltage will be what? It will be leading from the reference with 90 degree, correct? Because it has a plus j added to it, so it will lead, because my VL, if you know my VL is j omega Li. So with I am multiplying of j, that means I am moving in the anti-clockwise direction by 90 degrees. So the resultant will be my V, right? Because it is the phasor sum of VR and VL. My Vs is the phasor sum of VR and VL. So this is my resultant vector. This is basically my V. So magnitude of V is under root VL square plus VR square. Okay. So now what we can do is few things we can do. This magnitude is VL square plus VS square, that much is, it is just like a Pythagoras triangle. What about the angle? This angle has a name. Why? Because this is the resultant voltage, right? And the resultant current is here. This is the current and voltage. So this is the resultant voltage, that is this 5 sin omega t, and this is the resultant current. So the angle between them is defined as phi, and this phi is very, very important for us. So what is phi? So this is a right angle triangle, right? So I can write my sin phi will be equals to what? Height upon the hypotenuse. Height is VL upon hypotenuse, that is magnitude of V. Or you can write cos of phi is base upon hypotenuse. Base is VR upon magnitude of V. So this VL, like this right, VL is the magnitude basically. I'm talking about the side, like this theta are lengths, basically lengths of a triangle, right? So I'm talking about the values basically, not their signs as well, not their angles. So VL can be written as what? VL can be written as JIL into XL magnitude divided by what can be V? What can be V written as? V can be written as I is IL only, I into Z, magnitude of I into Z, or your sin phi will come out to be XL over Z. And what about the cos phi? Cos phi will come out to be what is this? This is I into R, correct? Magnitude of I into R into magnitude of V only. Magnitude of V is I into Z, correct? Because my V is what? V is I by Z, right? V is Z is what? V by I. So V will be what? I into Z. So that is what I am doing here. So this will get simplified to R by Z. Okay, very, very important relationship. Basically your cos phi is also known as the power factor. Okay, power factor term. Now here currently the power factor is the load. Our load is RL only, because the load and like source almost are connected together. So currently it is just, I will say, power factor, but power factor can be of two types. One will be for the source, one will be for the load. So in network theory, whatever we discuss, mainly unless and until specified, we will find out the power factor for the load only. In power electronics, there we used to find the supply power factor. Like this you will learn later on when you will go to study power electronics from me. Okay, so but in network theory we only discuss about the load power factor. In network theory we only discuss about the load power factor. Okay, so EC guys don't have to worry about the supply power factor. But power factor, the definition of power factor is basically the angle between the voltage and current, resultant voltage and current. Now the resultant voltage and current can be for any component, the supply, the load. So power factor, when just power factor is written, if just you have to find out the power factor, nothing else is written, that means by default you will understand you have to find out the power factor of load. Okay, you have to understand that you have to find out the power factor of the load. But the power factor can be, it is not like power factor is only for the load. Power factor can be found out for anything. Power factor can be for supply as well. Then what is the angle? Power factor is the cause of the angle between the resultant voltage and current. If they are asking you to find the power factor of the supply, that means you have to find out the angle between resultant current and the resultant supply voltage, resultant supply current and resultant supply voltage, if they are asking you to find the power factor of supply. So all of it depends. In this case, we are very lucky that my load and the supply, the voltage and the current are same. That's why the load power factor and the supply power factor both are same. But someday gate will frame a question, and if for the electrical guys it is very easy because they study about supply power factor later on in the power electronics. But for EC guys, if supply power factor came, they might get scared a little bit. That's why from the starting itself I am warning you what is power factor. So power factor indicates the phase relationship between the resultant current and resultant voltage. Basically it is the cause of the angle between the resultant current, that is theta I, and theta V. Okay, now this can be for anything, not only for load. It can be for source or load. Okay, it can be for anything, but generally by default we will choose this is the default option. If nothing is mentioned, we will choose the default as load. We will assume that if they are asking power factor, they are asking about the load. Now power factor can be of two types. One is leading power factor, lagging power factor. What does leading and lagging means? So leading power factor means where the current leads the resultant voltage, and lagging power factor means where the current lags the resultant voltage. Now in this circuit, what is happening? Can you tell me? Is this a example of leading power factor or lagging power factor? This is example of lagging power factor. Why? Because in this case the current lags the voltage, because it is an inductive circuit. Voltage is here, current is in the clockwise direction, so current lags the voltage. Same thing I have told here only, right? So if the resultant current for the lagging case, if the resultant current lags behind the resultant voltage, that means it is a example of lagging power factor. I hope it is clear now. It is example of lagging power factor. Okay, so formula is cos phi, and we will come to this active power. Don't have to worry about this. It is Vi cos phi. We will come to this. You can ignore this fact for now. What is Vi cos phi? All those things we will come to those later on. So few things about power factor. One more thing is that if you want to find out, like you can find out many relationships you can derive. Don't have to remember this, but someday or another all this will be getting used. So don't have to memorize, just see the derivation. How am I deriving this? So what is tan phi? Tan phi will be the height upon base, right? Height is VL, base is VR. So it is magnitude of VL upon magnitude of VR. So it will be I into Ji into XL. Ji into XL divided by I into R. So this will be XL by R. So this is also another relationship. Don't have to mug everything up, but the main thing is how am I deriving. So all this will be used. Someday only XL and R will be given, and they will say tell you to find the power factor. So what you will do? First you will do this XL by R. This will be tan phi, and then you will take the inverse. From there you will find the phi, and then you will do the cos of phi. So like that, like this question can be framed. Okay. So I hope you understand why I am writing this, because you should know how am I deriving these things. No need to remember, but if you remember, right, this phasor diagram, how am I deriving, then this will be helpful for you, and this will automatically be in your mind. Automatically this will be remembered. This is not an extra pressure. Automatically, like you will practice so many questions, automatically this will get into your head. Okay, so that is the thing over here. So next is this series RL circuit. So in series RL circuit we have the resistor inductor that share the same current. So here the voltage will be in phase with the current, but the resistive voltage will be across the same phase with the current, but the inductor voltage will be phase lag, will lead the current. That's why it is written here. That's what is written over here. Voltage across the inductor leads the current by 90 degrees. And your impedance will be R plus jXL. That is written over the phasor diagram is this, impedance triangle is this, that we have already derived, and this is the power factor cos phi z. Okay, and tan phi z is simply XL by R. Tan phi is simply the imaginary by the real component. So okay, all this is we have learned. So few more things we can derive. That first of all, it is a lagging network. It is a lagging circuit. That have we written is no, yeah. So power factor will always be lagging for inductive, overall inductive circuits. Power factor will always be lagging. So your phi, right, power factor angle can be written in multiple ways. So phi z. What is angle of z? Angle of z is phi z. It can be written as what? Tan inverse omega L by R, because XL is simply omega L by R. So here, right, what am I saying? Your cos phi, sorry, your tan phi is equals to XL by R. XL is what? Omega into L. So tan phi is equals to omega L by R, and your tan of phi z is also equals to omega L by R. That means what? That means your impedance angle and power factor angle both are same. Now generally students assume that they are the same quantity only. No, these things are different actually. This is the angle between the resultant current and resultant voltage. This is the angle of the impedance angle. But in this case, the impedance angle, and most cases impedance angle will be same as the resultant angle, power factor angle. Okay, things will change. When it will change, I will discuss. Okay, for now you understand that impedance angle and the power factor angle both will be same. Okay, what about the cos phi? If I want to write the cos phi in terms of the circuit elements, so cos phi is VR by V, right? This I have derived. It is simply R by Z, I into R divided by I into Z, R by Z. So R is R, Z can be written basically the magnitude of Z, right? So it is simply R square plus XL square. So you can also find out the power factor from this formula as well. So no need to remember all the formulas, just understand how am I deriving this. Okay, so this is a homework for you, that whatever you have learned about power factor, try to solve this, and this I will solve in the assignment solutions lectures. Okay, yeah. So one thing I just made a mistake in here, right? If I have mentioned by default, so yeah, here, right, I have made a mistake. So previously what I was telling, that by default you take the load power factor. No, by default, if nothing is mentioned, you will find out the source power factor. That is what I just remember right now. I just messed up there. It was a slip of tongue. So it will be by default you will find out the source power factor if nothing is mentioned, but maximum chance is there it will be mentioned. Don't worry, it will be mentioned. If it is not mentioned, right, then it will be MTA. In network at least it will be MTA. So that is what I have written here, over here only. So if here only I have written that if no information is given about the power factor, like where you need to find the power factor, whether from the source or the load, basically it will be with respect to the source only. So source power factor is also known as the input or input power factor. Okay, so what do you do? You find the input voltage, you find the input current, and you find the phasor difference between the input voltage and current. Okay, and then the phasor difference, you take the cause of that, and that will be your source or load power, source or input power factor. What will be the load power factor? You find the load current, you find the load voltage, you find the phase difference between these two quantities, then you take the cause of phi naught, and that will be your LPF, that is load power factor, and this will be your source power factor. Okay, so this is the difference between load and source power factor. Let's now understand another concept. So if I tell you to find out the currents in both of these circuits, will you be able to find out? So the first circuit, I have a DC source, and the second circuit I have a AC source. So in case of DC circuit, right, you simply do the KCL, and your current I will come out to be 3 minus 2, because 2 is outgoing current, incoming is 3, so remaining current will be 3 minus 2, that is 1 ampere. Here, will I be able to apply the same KCL, that I is equals to 3 minus 2? Remember, the input is AC. Here, right, I will not be able to apply the same concept. So you will say then, sir, KCL is invalid. No, KCL is valid. What is invalid? Invalid is you applying this algebraic addition. I have told you previously as well, we cannot do algebraic addition or subtraction. We have to do phasor. addition. Okay, and the first thing that you should ask whenever like the currents are given and it is a AC input is what is the phase angle of these currents? Sir, what is the phase angle? What is the phase angle? So I have not given you any phase angle, right? So that is a problem. So if no phase angle is given, you have to assume something and solve according to that. So you cannot simply do this KCL. It will be phasor subtraction. So here same thing is written over here, that in AC circuits performing addition, subtraction, multiplication, division requires the knowledge of phase of that quantity. Then only you will simply be able to do the phasor addition or subtraction. So if the phase angle of any one of the quantity is given, assume it as the reference and proceed, or you can assume your own reference. That also you can do. I will tell you later on. I will tell you about that later on. If no phase angle is provided, you are free to choose any one quantity as the reference. Generally, for series circuits, you choose the current, and for parallel, you choose the voltage. Same thing is written over here. To simplify the calculations, we select the quantity that is connected to the maximum elements in the circuit as the reference. To simplify calculation, we select which is maximum connected. So in this case, right, what can I choose as a reference? So this Vin is here, right? This Vin is here, that is connected across this voltage, across these terminals and these terminals as well. So what I can choose is I can choose the voltage Vin as the reference. In this case, particular example, it can be different as well. I will see which component is getting connected to most of the elements, that I will choose as reference. For instantaneous values, perform simple algebraic addition. So if I am doing simple algebraic addition, that means I am doing for instantaneous values. Instantaneous means it is a function of t at that particular point of time. At that particular point of time, t equals to 1 second. What is the current here? Then it is fine. Then you can do algebraic addition, subtraction. But we are not simply doing the we are not always talking about the instantaneous calculation. In GATE, very rarely they have asked for the instantaneous value. Someday they will ask the instantaneous value, and like most students will will not even understand that they ask the instantaneous value of the phasor value. Okay, so instantaneous value means what? The value of I2 at some particular time t, correct, at t equals to t naught. That is what instantaneous value is. So for that particular thing, you don't need any phasor knowledge, just simple algebraic KCL, algebraic addition, that's it. Okay, for instantaneous you don't need complex calculations, simple algebraic addition. But if you want to write the current, right, current I as a function of sine or cosine, okay, sine or cosine, that means then you have to write the phasor quantity. Okay, for a instant of time there is no problem, you can use algebraic addition. But for a particular sinusoid, if you want to write the voltage or current in terms of sinusoid, then you have to do phasor addition. So this is the homework that I will give you, and in the next lecture we will solve all these questions. So this is a 12th question basically. So we will solve this question basically. Now we will discuss about series RC circuit. So whenever I write like this, right, bar, so this is also a representation of phasor. That means we are doing phasor addition, not simple algebraic addition, we are doing phasor addition. So in this case, my Vin is simply what? Vm angle theta. So Vm I have assumed to be the Vm I have assumed to be the amplitude. Now what is theta? Basically I have assumed my current to be the reference, right? I is equals to Im angle theta, or I, first of all, I will be some Im sine omega t. I will be Im sine omega t. This will be my current, and in the phasor I can write this as Im angle 0 basically, sorry, Im angle 0. So of course there will be some theta angle, either it will be negative or positive, we will see that, but there will be some theta angle with the voltage, right? Because voltage is basically sum of the resistive component and the capacitive component. So there will be some angle with respect to the resultant current. It will not be 0. And of course for VR it is very simple, right? The current and the voltage both will be in the same phase. So in this case it will be VR angle of 0, because current and voltage, because here IR is also same only, because it is a series circuit, so it will be Im angle 0 only. So current and voltage will be same phase for the resistance. What about for the capacitance? For the capacitance, we know current leads the voltage. Current leads the voltage, or other way around, voltage lags the current. So it will be magnitude of Vc lagging the current. Current is at 0 degrees, so I will lag the current by what? By 90 degrees. By 90 degrees. So this can be written as Vm angle of theta equals to VR basically plus of minus j VC. VC is just the magnitude. So from here we can directly write the, not Vm, sorry, this will not be Vm, yeah, this will be Vm only. Yeah. We can directly write that my magnitude of V, that is Vm in this case, magnitude of V is equals to under root of VR square, just simple phasor diagram, right? Under root of VR square plus Vc square, which is equals to Vm square, Vm, okay? Remember, all these are not RMS, in our case these are all peak values. So how you have defined your phasor, it will depend. So this is just all phasor quantities. When I will come back, that is the ultimate quantity, sine or cosine. What about the angle? What is the angle between the resultant voltage and current? So angle is the theta, right? And I am talking about the supply power factor. So angle theta will be equals to what? It will be simply equals to the y component by the x component. Now here it is lying where? It is lying in the fourth quadrant, and I have told you, right, for any linear passive network, either you will lie in the fourth quadrant or in the second quadrant. That's why you don't have problems with the angle for this basic things. But whenever you lie in the third quadrant or the second quadrant, then you get the problem of calculating the angle. That's why we have cleared the basics. So if I am lying in the fourth quadrant or in the second quadrant, basically it will be minus j, okay? It will be minus j. So this will be basically negative of tan inverse magnitude of Vc divided by magnitude of Vr, or magnitude of Vc is simply I into 1 by j omega c, correct? Magnitude of Vc is I into tan inverse I into xc divided by magnitude of I into r, okay? So this will be minus of tan inverse xc divided by r, okay? This is how you can calculate. Or x, what is xc? Xc is 1 by omega c, if you remember. Xc is 1 by omega c. So this can be written as 1 by omega rc. This also you can do 1 by omega rc. This will be your what? This will be your minus tan inverse 1 by omega rc. This will be your phi. But what is your impedance angle? What is your impedance angle? So your impedance angle is what? Z will be equals to what? So if I write here this equation, right? If I write this equation, that this is my resultant input voltage V in, and this will be I into R plus I into xc. Xc is what? 1 by j omega c, correct? Okay. So my V in by I in, here I can write V in by I in will be simply equals to R plus 1 by j omega c. So this will be equals to R minus j divided by omega c, okay? So from here you can find out your impedance angle. Your impedance angle will be, sorry, your magnitude of the impedance will be R square plus 1 by omega c whole square, and your phase angle will be tan inverse omega 1 by omega rc, okay? This will be your phase angle and this will be your magnitude of the impedance, correct? Will this be? No, this is not correct. There will be a negative sign as well. Why? Because this is lying in the fourth quadrant, okay? This is lying in the fourth quadrant. I hope you remember that thing, okay? So impedance angle is this. This is my phi z, and this is same as the power factor angle only. Theta z, same as the power factor angle, okay? So what will be the phasor diagram? So for the impedance, the phasor diagram will be something like this. R will be here, reference, and minus j means I will go in the clockwise direction. This will be minus j by omega c, and the resultant will be somewhere here, vector addition basically will be somewhere here. Okay, so this will be the phasor addition, that is z angle theta z. Okay, what about the phasor diagram for voltage and current, right? For voltage and current, this was the impedance triangle basically. What about the phasor diagram for voltage and current? So voltage, it is a series circuit, so I will assume current to be in the same phase, reference current to be in the reference, right? So here my current is in the reference. Okay, current is in the reference and my voltage is here. This is my current, right? This is my current, and my drop, that is Vc will lag the current, because current is same across the capacitor, and I know capacitor current leads the voltage, so voltage will lag the current, capacitor voltage will lag the current, so it will be here, capacitor current will be somewhere here. This is my IC, so, and the resultant will be this. This will be the resultant, that is what, sorry, this is not IC, sorry, this is IC is same only, this is VC, sorry, this is VC. Okay, this VC and VR, right? VR is in the same phase, correct? VR and I will be in the same phase because it is resistive. So the addition will be basically, sorry for this, this is not the addition. Addition is like my voltage V will be addition of vector addition of VR and VC. So it will be somewhere here. This will be V, and you see that right now my angle phi, it is negative because I am lagging. So not lagging, I am leading basically, because my current is leading the voltage. So here my current is leading the voltage. Current is leading the voltage. Okay, so current leads the voltage in this particular circuit. Current leads the voltage in this particular circuit. So again, if you want to find out the cos phi, it will be same formula only, like you can derive cos phi will be equals to VR by V. Basically you just apply the triangle, right? Cos of phi will be based upon hypotenuse, VR by V. V is the hypotenuse. I am talking about the magnitudes. Remember, whatever I am talking about the magnitudes. So what is VR? VR is I into R, and V is I into Z. For a series circuit, it will be R by Z. So this formula is only valid for a series circuit. This, right, don't mug this up. Only valid for series circuit. Once I will come to parallel circuit in the next lecture, this will change. But what will not change? This will not change. This will not change. Okay. All right. Even if you like, this can also change. What will not change? Definition of phi. Definition of phi is angle between voltage and current. Remember that much. Draw the phasor diagram. From there you find the cos phi. That will be helpful. If you just mug this up, then I will give you some circuit. For that, this formula will not be working. Okay, this will not be working. So just be careful regarding that. So here, right, it is R by Z, but what is my Z? So Z, right, is the magnitude. Z is this. Okay, so I can replace my Z with this, under root R square 1 divided by omega C whole square. Okay, so this is my Z basically. So this is a leading circuit. So capacitive circuit is a leading circuit. That is what is written over here. Resistor and capacitor share the same current. It is a series circuit. Voltage across the resistor will be in the phase with the current. Voltage across the capacitor lags the current by 90, or I can say current leads the capacitor voltage by 90. So IC leads VC. So it basically acts as a leading circuit. Why? Because of the capacitance. Previously I had inductance, that's why it was acting like a lagging circuit. That is the difference between a capacitance and a inductance. Okay, so power factor, generally, since the current leads the voltage, power factor will be leading. Now I forgot to mention, whenever you write the power factor, right, you write the power factor, that is fine. Power factor is written here, right? I have defined the power factor somewhere here. Yes, here. So I forgot to mention at that point of time, you have to say whether it is lead or lag. That also you have to write in brackets. So this is not that important for electronics students, but for electrical students, very important. This thing is very important for electrical students. What do I mean? So if the resultant current leads the resultant voltage, then cos phi, because you know, right, if your phi is positive or if your phi is negative, cos of that angle, cos of any negative angle and cos of positive angle, both will yield you the same result. That is, cos of minus phi is equals to cos of phi. So we will not be able to detect whether it is a capacitive circuit or a inductive circuit. To resolve that problem, what we do, we generally in brackets write whether it is leading or lagging. So if let's say your overall circuit is inductive and power factor is coming out to be, phi is coming out to be plus 36.86. So you do cos of 36.86 and it comes out, its value will be what, cos 36.86 will be something around 4 by 5. Okay, it will be 0.8. And as phi is positive basically means your voltage is leading the current, right? So, and bracket I will write here, this is a lagging circuit. This is a lagging circuit because this is overall a inductive circuit. If the same thing, if my phi is minus 36.86, you put in the calculator cos of minus 36.86, right? What you will get? You will get as 0.8 only. So the information about the negative sign gets lost. So how do I show that information? I say it is a lead. Why lead? Because angle is negative, that means my current is leading the voltage. My current is leading the voltage, that means it is a capacitive behavior, that means it is giving a leading behavior. So that's how we represent the negative sign basically, because the information about the negative sign goes away. To explain that, we write either lagging or leading in brackets. So here it will be cos phi, in this case it will be cos phi leading. Okay, so this is the basically, these are all assignment questions. Please try on your own, and in the next lecture of course we will solve all these questions. Okay, so next just one more topic is left, that is the series RLC circuit. The series RLC circuit is left, so we will solve we will derive the expressions, and after that we will wrap up our discussion. So let's do the analysis here. So I am adding up like this, simply this is KVL, right? This is simple KVL. So all these are phasor quantities. So my current again is the reference, current is the reference, that is Im angle of 0. Okay, so this VR will have its magnitude, that is I into R, and of course angle will be 0 only. Okay, what about the voltage? Now VL will be replaced with plus J into XL and VC will be replaced with minus J into XC. I hope you now understand why it will be replaced with minus J and XL. Of course, don't forget there are the currents as well, I and I. I hope I don't have to explain why they will be replaced with minus J and plus J. Now you can write here that your V will be I, if I take the common, this will be R plus J XL minus XC. Okay, so your V by I, basically V by I, because I is just a phasor quantity, V by I, the phasor quantity, the impedance Z will be coming out as, resultant will be coming out as XL minus XC. Now right, I cannot conclusively say in which quadrant it will lie. So if XL is greater than XC, then it will lie in the first quadrant. Then my phi, that is the impedance angle, and the power factor angle will be this value, tan inverse magnitude of absolute value of XL minus XC divided by R. Okay, and my phi, if my XL is less than XC, if my XL is less than XC, that means my phi will be minus of tan inverse. Now if, as I am calculating the absolute value, it does not matter whether I write XL minus XC or XC minus XL, because ultimately it will give me the positive output. So very important, right? Why? If my X is greater than XL, that means overall this quantity will come out to be negative, and if this quantity is negative, that means in which quadrant I am lying? Fourth quadrant. If this quantity is positive, that means I am lying in which quadrant? First quadrant. So I hope the angle and quadrants are all those clear. That's how the angle is there. That's how the angle difference will be there. Okay, so we will analyze each case at a time. So what will be the impedance? Basically impedance magnitude. So impedance magnitude, right? It is what? It is basically R square plus XL minus XC square. It does not matter if you write XC minus XL or XL minus XC whole square, because ultimately you are squaring it. So negative will become positive only. It does not matter. So I can rewrite this r square plus omega into L minus 1 by omega into C whole square. Okay, this is my representation. So my phi z will be what? Phi z again the same thing, right? Either I can write xl minus xc, or you can rewrite the xl minus xc as this. Okay, there will be two cases here, again like two cases. Phi z can have two values, so this, right, this can be rewritten. I will just copy and paste this thing. Okay, not delete, sorry, not delete, copy and paste this thing. Phi z here can be two things here. So here first one will be, this can be rewritten as tan inverse magnitude of omega L minus 1 by omega C divided by R. Okay, or this will be equals to minus of tan inverse magnitude of omega L minus 1 by omega C by R. Okay, so like this is also another form to represent. So you will have three cases. So first case is where my XL is greater than XR. So my XL is, sorry, not XR, XL is greater than XC. So basically it means the voltage component of, if I multiply I on both sides, because current is same across both inductor, capacitor and resistor and the supply. Current is same, right? So if I multiply I on both sides, so I am multiplying same quantity, that means I into XL is greater than I into XC. That means your VL, magnitude of VL is greater than magnitude of VC. That is what it is reflecting over here. So VL is the component that will lead the current, right? Because current is the reference. So this I into R will always stay here no matter what, because it will be in the same phase of I. But VL, the magnitude, the length of VL will be higher than VC. So ultimately what will happen? So it is the resultant of VL minus VC, right? So ultimately as VL is higher, so my resultant will be somewhat leading from the current. So the resultant voltage is leading from the current, or the resultant current is lagging from the resultant voltage. That's why overall it is a inductive behavior. And intuitively also you can understand that as XL, inductive reactance is higher. What more hint do you need? As the inductive reactance is higher, that means it will behave as a inductive circuit, inductive behavior. Okay, so that is the ultimate point that you need to understand. So values already have discussed. So again VL will be greater than VC. Here in this case your impedance angle will be positive and your power factor angle will also be positive, and your power factor will be lagging, overall lagging circuit, because it is behaving as a inductive circuit. Okay, this is your power factor, it will be lagging. Power factor will be what? Again you can like write from the this triangle, it will be either the this component upon this component, right? If I want to write the cos phi will be what? The base upon the hypotenuse. So what is base? Base is VR upon hypotenuse is magnitude of V. I'm just talking about magnitude right now. That is equals to I into R divided by I into Z. So it is again R by Z. It will not always be R by Z. It will not always be R by Z. Okay. So this will be equals to R divided by, what is your Z? Z is one formula only, right? What is the Z? Z is R square plus omega L plus 1 by omega minus 1 by omega C whole square. Okay, so this will be the value basically. This will be the value. This will be the phasor diagram. What will be the impedance triangle? Impedance triangle, I will just draw here. It will just mimic the phasor diagram only. So if this is the R, okay, my XL will of course lead. Okay, just I don't have enough space, so I will write here only. So this is my R. And what is XL? XL is plus J. XL comes with plus J, right? inductive reactance is with plus J. So it will lead the resistance. So it will be somewhat here, okay, and the capacitive reactance will be somewhere here, correct. So your inductive reactance is here and capacitive reactance is here, and of course the lengths matter, right? Do matter, lengths do matter. So size does matter, okay. So it's not like size does not matter, size do matter, okay. So here the size of, or sorry, not those kind of jokes. So here the length of XL is higher than the length of XC. So it is higher, right? Overall the summation vector addition, this the resultant will be somewhere here, right? Because the resultant, this XL minus XC will be somewhere over the R. So the resultant of this XL minus XC and R will be somewhat like this, correct? Vector addition, simple vector addition, that's it, simple vector addition. So this will be the impedance Z angle theta Z, okay. So Z is under root R square plus omega L minus 1 by omega EC whole square, and angle I have already discussed. How to find out the cos phi and tan phi also you can do. Next case I will do bit fast this time. So this time XC is greater than XL. So again if I do the same manipulation, that I into XC is greater than I into XL, that means what? That means basically VC is greater than VL. That means I will go downwards. I will go downwards. So overall it will behave as a, it will have a capacitive behavior. Capacitive behavior. So if it has a capacitive behavior, then overall my circuit will have a leading behavior. Leading behavior. Overall my circuit will have leading behavior. That's it. Overall my circuit will have leading behavior. Again the same formula, whatever, like previous thing I forgot to derive the magnitude of V. So what is the magnitude of V? It is same only, right? I hope you understand, like this is VR whole square plus the resultant VL minus VC whole square, okay, VL minus VC whole square. So here also same does not change. This formula will not change. Magnitude of V will not change, but in which direction? It is in downward direction now. So magnitude of V here is under root VR whole square plus VL minus VC whole square, okay. So yeah, that's it basically. Like angle, same thing only. This time angle will come out to be negative. That is one thing. Your angle will come out to be negative because it is a leading circuit, leading behavior. So angle will be negative. From here also you can understand XL minus XC, right? So it is in the fourth quadrant. So if it is in the fourth quadrant, so it will be negative. That I have already discussed. The phase angle I have already discussed, right? So power factor again, formula will be same. Formula will not change. Cos phi will be same only. Cos phi will be same. It will not change, okay? Because cos phi, like cos of any angle is positive. Sorry, cos of any angle, yeah, cos of any angle is positive for our case because we are either lying, our range of phi is from minus 90 to plus 90. If my range of phi is from minus 90 to plus 90, in that range cos is always positive. So this will be always positive, but in brackets I will write leading because it will behave as a leading circuit. Now there is a third case where both of them are equal. If both of them are equal, basically both are cancelling each other out. So if XL is equals to XC, basically, then my I into XC is equals to I into XL. That means my VC is equals to VL. That means my, what is the magnitude of V? Magnitude of V was, the formula was magnitude of VR whole square plus VL minus VC whole square, right? So this becomes 0 because VL is equals to VC. So ultimately, magnitude of V is equals to VR only. So magnitude of VR is magnitude of V only, okay? So ultimately, your resultant voltage and resultant current both are in the same phase. So it behaves as a purely resistive network. That means phi is 0, and if phi is 0, that means cos of phi is 1, cos of 0 is 1. Also it is known as unity power factor. Now we have inductance and capacitance. Those are there. Inductance and capacitance are there, okay. But still, I am observing that it is behaving like a resisted network. So even though your circuit can contain reactive elements, somehow you choose a frequency and that frequency is actually known as the resonant frequency. This behavior we will study, like we have a chapter in this behavior, okay, that is known as the resonant frequency. So we will obviously study the chapter resonance. From there we will do, okay. So in this chapter basically we take the condition of resonance where the voltage and like the voltage and current are in the same phase. So although there are reactive elements, there can be some frequency. So what is the frequency? How can you write the frequency? Your XL is equals to XC. So basically your omega naught 1 by omega naught into C is equals to omega naught into L. So omega naught whole square is 1 by LC, or your omega naught is 1 by under root LC. So this is known as a resonant frequency. We will discuss about this later on, but for a particular frequency this condition can happen, okay. So even though your circuit is containing reactive elements, it can behave as a purely DC circuit. So that is what is written over here, and all the phasor diagrams, all the impedance diagram are also shown. So impedance diagram I have not shown you. So in this case, right, in the leading case, what will be the impedance diagram? So in the leading case, I will just copy this thing, okay. In the leading case, if I just copy this thing, right, this is the impedance diagram. So I will write here impedance diagram. Have I drawn the impedance diagram? I don't feel I have drawn the impedance diagram. No. Okay. Impedance diagram. So the impedance diagram in the resistive, like in the capacitive case, it will be somewhat like this. So again the size, not the size of impedance will be lower. Sorry, of the inductive reactance will be lower than the capacitive. So capacitive reactance will be higher, that is mentioned right here, mentioned. So capacitive reactance will be higher. So overall your resultant will be not in the upper side, it will be in the downward side. So overall your XL minus XC will be somewhat here, XC minus XL, or XL minus XC you can write, but I am just showing you the positive number. So XC is higher, so it will be XL minus XC, and overall the resultant will be somewhere here. This will be the resultant of the impedance, right, impedance triangle. So this is the impedance triangle, okay. So I hope you have understood this point. And for this particular circuit, so for this particular circuit, right, XL minus XC is equals to 0 because XL is equals to XC. So for this particular circuit, the impedance triangle will be exactly here, right, size is same, so size is same, or the length is same, sorry, like if it is a double meaning thing. So here XL is equals to XC, that means both of them cancel each other out. If both of them cancel each other out, your impedance becomes R only. Your impedance becomes R only. Z is equals to R only because XL minus XC. So Z is equals to what? R square plus XL minus XC whole square. So it will be R only. Magnitude of Z will be simply R only. Okay. So it will behave as a purely resistive network. That is what is written over here. So these things you can read, find out the angles and all those things. And like if for a complex network, you already know for a normal resistive network, if I have multiple impedances in series, it gets added. Here also same thing. Here for a complex network, the Z equivalent will be, if it is a series circuit, it will be Z1 plus Z2 plus Z3 and so on. For a parallel circuit, same rule, that is 1 by Z equivalent will be 1 by Z1 plus 1 by Z2 plus 1 by Z3 and so on. Same rule for purely resistive network, whatever you have learned, it is the same rule. Now these are the questions that I want you to leave out with, okay. So you can solve these questions, and in the next lecture we will basically solve all these questions, okay. This is the 15th question, and I have already discussed about power factor. So this power, right, you ignore, this power you ignore. So we will discuss about this power in the complex power chapter, okay. This is the last question. So in the next lecture we will basically solve all the questions. So you can take the screenshots, whatever I have shown the question, you can pause the video, take a screenshot, solve the questions, and in the next lecture we will solve all the questions. So I hope you have enjoyed this lecture. If you did, make sure to comment down below. Make sure to comment in the first lecture of AC analysis that you are enjoying this whole content, so more people can watch. So yeah, I hope to meet you in the next lecture. Until then, happy learning.